Hi everyone. So our presentation is going to be on the straight edge and compass constructions. My name is Jericho Casve,
My name is George Barraza.
and let's begin. We're going to first start off with defining what a straight edge and a compass is. So on the screen, you can see what the definition of a straight edge is, and essentially there's two different ways to think of it. You can think of it by starting off with a ruler, and a ruler has markings on it. And so a straight edge is basically just a ruler without markings, but think of it more as like this infinite ruler, basically, with no markings, if you will.
Our next slide is on the definition of a compass and construction of a circle. So we need to define a circle to define a compass. So our definition of a circle is a circle, or actually, we got this from Professor Vega's book. We have a circle is a set of all points on a plane that are the same distance r from a given point. The number r is the radius of the circle, where O is the center. And our compass is this figure down below, and we have it defined as it is an infinitely large radius without markings on it, similar to how we define the straight edge. And it is used to construct circles or arcs given 2 points, where one point is used as the center of the circle and the other point is on the circle.
Okay, so we're going to begin with defining what a constructible number is. And so on the screen here, you can read that the constructible number is a real number if there's this way of constructing a line segment using our straight edge, and then a compass that defines that line segment used with the straight edge as r, which is going to be the length of that line segment, which is the radius of that circle that we used with our compass. And so we'll see more examples on how that looks visually through GeoGebra. Um, in our book, we defined that, or we denoted the set of all constructible numbers to be this fancy looking K. And then we'll see through our examples, such like some constructible numbers like the square root of 2, and then non-examples of, like, for example, here, the cube root of 2 later on.
So now we're going to go into constructing a perpendicular bisector. We've all taken 160, or we're all taking 161, so we know what a perpendicular bisector is. But just in case you forgot, we have the definition from Professor Vega's book. Perpendicular bisector is a line given a line segment AB. There's a point P that is equidistant to A and B. So we have PA is equal to PP. So in other words, we have that the point P is a perpendicular bisector of the line segment AB, if and only if PA is equal to PB.
Yeah, and so to build off of what George said, when we get into the next image that you'll see, we're just going to note that the distance between our point A and point B is the same distance as it would be with point B to point P. And that's because when we look at the two different circles, one with the center point B and one with the center point A, they share the same radius, which is that distance AB.
So this is an example, or this is how we constructed a perpendicular bisector given the tools in our arsenal, which is a straight edge and a compass. To begin, we were given a line segment AB, and from there we constructed the circle C sub AB, with A being the center and B being a point on that circle. Similarly, we did the same thing with B being the center of the circle and A being a point on there. We see that they intersect at P and Q, and then from there we can construct a triangle APB, and we can see that AP and BP are equal distance because they're both have radius AB, like Jericho was saying earlier.
Nice. So to start off with, using one of our definitions of the constructible number, we're going to go ahead and try to construct the square root of 2 with this new knowledge on how we constructed our perpendicular bisector. So first off, we have 2 points A and M. And so what we're going to go ahead and do is take our straight edge, and we're going to take those 2 points on our straight edge and then create a line segment through it. So then we'll have this line segment AM, and we're just going to denote that length to be 1, because why not? It'll be useful when we get to square root of 2. So now that we have that, we can go ahead and take our center point M and then use our compass and have that point A be the outside of that, or be a point on the circle with center M. And we're going to go ahead and draw a circle, which gives us a point on the opposite side, which is B. And so we have now, using a straight edge, we can extend the line segment AM to now AB.
Now recall the perpendicular bisector. We get the line PQ is perpendicular to the line AB, and we're going to use this in our example to construct the square root of 2. So here we get, this is our, from 2 slides ago, we have that AM is length 1, and then we extended it to get our line B. So now, since we constructed the circle, we have AM and RM, which are both length 1 since they're the radius of our circle, with M being the center and A being a point on that circle. So now we can construct the line AR, which will be the hypotenuse of our triangle AMR. And then we can use the Pythagorean theorem to solve for that missing side length.
And so here's just like a quick recap from the book that tells us like how we can use the hypotenuse and how that's found. So we're just using the Pythagorean theorem, using the hypotenuse, and so we have line segments. So in this case, right here, we have a squared plus b squared is equal to c squared, but in the previous case, it was just basically those line segments that we just know as a, b, and c. So then right here, we get that, 1 squared plus 1 squared gives us 2, and then that's how we get the square root of 2, because our lines right here is square root of 2, which is equivalent to 1.4. So yeah, that's how you get a constructible number of the square root of 2. And by definition of constructible number, it's just basically using a straight edge and a compass to construct that number, and so we did that.
All right, now we're going to define a constructible angle. An angle is constructible similar to constructible number. It's constructible if we can construct it using a compass and straight edge. So for example, with the perpendicular bisector, we were able to construct the angle 90. So we know that 90 is a constructible angle.
Yes, sir. And so we're just going to go ahead and recall what the definition of an angle bisector is from the book. So here's that little recollection of that. It's basically just you have a ray, and then you take that ray through basically a line segment using the right.
Here we're given an angle, and then there exists a ray that goes through the angle such that the two angles that it bisects are equal to each other.
Yeah.
So here, here we have, similar to the image before, we have our perpendicular bisector. So we know we constructed the angle 90, and from here we can so this is how we're constructing the angle bisector. So here we're going to start by constructing the circle C sub RB, with R being the center of the circle and B being a point on the circle. And then next we're going to construct a similar circle, but with B being the center of the circle and R being on the circle. And similar to the perpendicular bisector, we get that they intersect at points C and D. So we're going to draw a line segment through those points. And that line segment is going to be our angle bisector. And as we can see, we get the angle 45 degrees. So now we know that we can bisect the angle 90 to get 45 degrees, and we get that 45 degrees is a constructible angle because we were able to construct it using only a compass and straight edge.
Yeah, so this is just another way to verify that the angle 45 is constructible. And so we have this theorem that we found, which is called the constructible angle theorem. And so it's basically saying that an angle alpha it's constructible if and only if you take the cosine of that angle, and that whatever number we end up getting taking that cosine of the angle is a constructible number. So using the constructible number angle theorem, we can take 45, take the cosine of 45, and we'll see that it's the square root of 2 over 2, which is a constructible number since it's a real number. And so we can conclude that further that 45 degrees is a constructible angle.
Another example of a constructible angle is 30 degrees. We know we can construct a equilateral triangle, which gives us the angle 60. We get that the angle 6 or we get that 60 degrees is a constructible angle. So now we're gonna bisect that. But instead of doing it that way, we're gonna first go about it using the theorem that Jericho mentioned. So we know that the cosine of 60 is 1/2, and we know that 1/2 is a constructible angle. So we get that 60 is also a constructible angle.
I wanted to clarify when George said 1/2 is a constructible angle, he meant one
Oh.
half is a constructible number because
Yes.
1/2 is a real number.
Mhm.
And then to build off of what George said, when it's using the construction of an angle bisector, as we saw with 45 and 90, so we took 90 degrees and then we used the angle bisector to get 45 degrees. And then we just kind of verified using the constructible number angle theorem. And so here we're using the angle bisector on 60 degrees since we know 60 degrees is a constructible angle. And we get that it's 30. But let's verify that this is actually a constructible angle. And so we take the cosine of 30, which gives us the square root of 3 over 2, which we can conclude is a constructible number because the square root of 3 over 2 is a real number.
Thank you.
Yes, sir.
All right. On this part of our presentation, we haven't finished it yet, but we're going to include examples of angles that are non-constructible. So, for instance, we mentioned earlier that the cube root of 2 is non-constructible, and then in this slide, we're going to kind of go into why that is.
Okay. So now let's get into something really fun that well, at least we think is super fun, which is going to be the construction of a regular pentagon. But before we begin with constructing a regular pentagon, we have to know exactly, by definition, what that is. And so first we want to define that a pentagon is going to be just a five-sided polygon, or we could think of it as a fivegon. And so we know that the sum of the internal angles in a pentagon is going to be 540 degrees. And we know that because in class we learned how to find these like internal angles and the sum of the internal angles. And just by definition, you can just look it up and be like, oh, yeah, it's 540. But we are trying to construct a regular pentagon and not just any five-sided polygon. So a regular pentagon has this extra condition, which is that all the sides need to be equal and that all the interior angles share this angle measure of 108 degrees. And so when we go ahead and construct our regular pentagon, we're going to be using a lot of circles to really verify that they share the same radius. And so that will help us get this extra condition, which is that all the sides are equal. So, do we just open GeoGebra now?
Yeah, so now we're going to get into it.
Yeah. Okay. So right now, George is going to go ahead and take 2 points on our like plane. Let's go ahead and take out the grids. So we're going to take 2 points, A and B, and he's going to use a straight edge to go ahead and construct the segment AB. And then what's going to happen next is that we're going to take a compass and we're going to take a center point A and extend that to B and do the same thing.
Here, we're practically just taking the perpendicular bisector of this line segment, and we're doing that to find the midpoint between, or we're to find the midpoint of the segment AB.
Mm-hmm. So we're going to take, so now that we have the intersection of these two circles, we have these 2 points C and D. And so we can use a straight edge again to go ahead and construct that line CD. And that line CD and intersects the line segment AB, which is going to be the point E.
So now that we have the midpoint of the line segment AB, we can get rid of all the stuff that we're not gonna need. So we can get rid of these circles,
Point C and D.
So now we're gonna construct a circle with E being the midpoint and A or B being or A and B are gonna be points that lie on that circle.
Mm-hmm. So we're going to be using a compass to be constructing this part.
Mhm.
And so that will give us 2 points since the circle intersects the line that contains the point E.
So now we're gonna construct another circle using our compass with A being the midpoint or A being the center of the circle and E being a point that lies on that circle. And then here we're gonna construct the perpendicular bisector to find the midpoint between the segment AE. So we get these points where the circles intersect,
Mm-hmm.
and then we get the line that goes through those intersection points and the midpoint H.
Mm-hmm. And so now we can go ahead and hide those. And then also we can add the points on the intersection of the circle and the line containing E, because it will be useful for when we get our first point that's on the pentagon.
So now that we have our midpoint of the line segment AE, we're going to construct this little circle with H being the center and A and E being points on the circle. And then we're going to construct the line HI so we can find this intersection point between the line and the circle where H is the center and A and E are points on the circle. So we get this point. And then now we can get rid of some things that we don't need anymore. Get rid of this circle, these point, or not that point yet. So we're left with this.
Yes, sir.
And now we're going to construct a circle with I being the center and J being a point on the circle. And these 2 points are going to be points on our pentagon, points for our pentagon.
Those points being K and L.
And also M.
And then we have that point M. Yes. So those are going to be our 3 points that construct our polygon or our regular pentagon. Yes, sir.
Now we can also get rid of these points A and B. We're not going to need them, as well as this segment. So we're left with this. To confirm that KM and ML are the same, have the same length, we can use the radius of a circle. So K and M have the same radius as well as M and L.
There you
see
go.
they all have the same radius because if M is the center point, if the center of the circle, we get that K and L are on the circle, implying that they have the same radius.
Yeah. So let's draw some segments that with our straight edge that go through K and M, and also L and M. So those are going to be our first 2 sides of our regular pentagon. Now that we have a circle that has the center K and a point on M or M on the circle, we can actually take that other intersection point, which is going to be N, and that will give us the segment using a straight edge KN. And then we could just do that again with center point N and a point K on the circle, which gives us a new point O on that circle. And so the radius KN will be equal to NO using our straight edge. And then we'll do it again.
We can do it again, yeah.
Yeah. And
just to confirm, so we get O as the center of the circle, N and L being points on the circle.
Mhm.
And as we can see, all our distances have the same radius, implying that all our side lengths of our pentagon have the same length.
So it meets the condition, well, at least we think it meets the condition of it being a regular pentagon, but we're going to go ahead and verify once we hide all our circles and all the mess that we have created. And we're going to go ahead and take the Internal angles, yeah.
Yes.
And we're gonna verify to see that they all are 108. Which they are, and so 108 what times 5 is 540.
Mhm.
So that gives us exactly what we needed. We have a pentagon, and now we have the extra condition of it being a regular pentagon, which gives us the angles 108. So we can now hide that.
So now we can also find some other angles using this construction, which we only use compasses and straight edge. So since we're able to construct this pentagon using only a compass and a straight edge, that implies that the number 108 is a constructible angle.
Yes, sir.
So now to find more constructible angles, we can construct these isosceles triangles from the one of them being the triangle MKE, another one being the triangle MEL, and so on. And as we can see, if we take the angle from KEM, we get the angle 72.
Yep.
So this shows that the angle 72 is also a constructible angle because we were able to construct it again only using the straight edge and compass.
Mm-hmm.
And in addition, we also have that the angle 54 is also a constructible angle.
Yeah, and then looking at the bottom triangle also, when we have that angle being 72, we actually did an angle bisector like thing. So now we can actually get another constructible angle, which is going to be dun dun dun. Oh, that is
We got to make this
not.
point. Hold on. Sorry about that. Sorry about that. We get the angle.
Dun 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 36. So an interesting thing actually is that we constructed angles 108, 72, 54, 36, 90, and 45.
Yes, because the angle NPE right here is a 90-degree angle.
Mm-hmm. And then an interesting thing that we have learned through our project actually is that these are all divisible by 3, right?
Yes.
By the degree 3.
They're all divisible by, yes, the degree 3.
So in our paper, we kind of just covered like how constructible angles, there's this theorem where constructible angles are multiples of degree 3.
Mhm.
And so this kind of helps.
Piggybacks off of it.
Yeah. Yeah.
So thank you guys for watching. Real quick before we end, we're gonna show you guys our references. So we're not
Yeah.
plagiarizing, I guess you would say. So here are our references. And yeah, thank you guys for watching.
Thank you. 2 sets of thank you. Thank you.